welcome to our lesson today. We are still on forces, and the last time we looked at average speed. Average speed was given by total distance divided by total time. Now we want to advance and look at motion equations based on our average speed that we looked at in our last lesson. And we are going to call them equations of linear motion. Now, just a reminder, one of the effects of force is that it can cause motion. And we want to narrow down to only one type of motion, which we are calling linear motion, which simply means motion in a straight line. Motion in a straight line. Now, these equations that we are talking about are used to describe motion in a straight line. And as we are going to advance, you will realize that when we talk about motion in other directions, the equations will also change respectively. Now, just to define these equations, they are equations used to describe motion in a straight line. They give us a relationship between velocity, both initial and final. We shall also consider acceleration. We shall look at the time taken as well as the distance covered. These equations relate both initial and final velocity. We shall also incorporate acceleration, the time taken, and the distance covered. We have about 3 equations. Equation 1. It gives the relationship between initial velocity, which in our case we are going to write as u, Number 2 is the final velocity. We are going to call it v. Then we have acceleration. We call it a. And then we have time taken. We call it t. And it's good to note that this equation has no distance factor. No distance factor. The equation has no distance factor. Let us now derive it. We say acceleration is equal to final velocity minus initial velocity, and this one we divide by the time taken. Call it first star. Now let us multiply both sides of star by t just to get rid of the denominator, and this one will give us on this side we multiply by t. We can cancel where possible to get at is equal to v minus u, and then we can make v the subject of the formula. Where we subtract or we add u both sides, and that will give us at plus u is equal to u plus v minus u. We collect the like terms. U plus minus u is 0. Therefore, this will yield something like this. V is equal to u plus at. See, we start from the final and the initial velocity. We relate them by dividing by the time taken, and what we get is acceleration. That was our first equation. Then we want to get rid of the denominator. Therefore, we multiply by t both sides and cancel where possible, so that we end up with at being equal to v minus u. Then from there, we can decide to make v the subject, and that will be achieved by adding u both sides, so that now v is equal to u plus at. Now, you can see the quantities that we are relating in our equation number 1 are the final velocity, initial velocity, we have acceleration and time factor. And you can see that from our first equation, distance factor is conspicuously absent. Equation number 2 gives us the relationship between it gives the relationship between distance covered in our case we called it S, time taken, small t, acceleration small a, and initial velocity, or what we call u. Again here we note that the final velocity which we called v is not accounted for. That final velocity will not be captured here. However, we shall have the distance covered, time taken, acceleration, and the initial velocity. Now, let us derive the equation number 2, and again we start from average speed, which is given by initial speed plus final speed, and this we divide by 2, which will give us u plus v over 2. Now, from this one, distance is given by average speed multiplied by time. So we take from that equation, average speed is given by u plus v over 2, and we want to multiply this by time, which will give us u plus v over 2 t is what we call S, which is our distance. But we recall from equation 1, v is equal to u plus at. So we substitute for v so that we can get S is equal to U. In place of V, we are putting this value plus U plus AT. The whole of that should be divided by 2. Then they should be multiplied by T. Let us try and open the brackets. S will be UT plus UT plus AT squared, and all this should be divided by 2. Let us correct the right terms. S will be 2 UT plus A squared plus AT squared, and this one we are dividing by 2, and therefore S will be given by UT plus a half AT squared, and this is our second equation of linear motion, relating distance covered, initial speed, time taken, and acceleration. So clearly, V is not accounted for. V is actually not accounted for. We look at the third and the last equation, which we are going to call equation 3. Equation 3. And equation 3 provides the relationship between one is the initial speed, 2 is the final speed or velocity, if you wish. Then we have 3 is the distance covered. Again, we note time factor is not incorporated. Again, time factor is not here. We want to try and come up with it with the equation. And we start from the first equation of linear motion. V is equal to U plus AT. Now, squaring both sides. Squaring both sides, squared will be U plus AT squared, which will be U squared plus 2 AUT plus A squared T squared. Then we want to factor out. Yeah. We factor out 2a where possible, so that we are going to get v squared being u squared plus 2a. Here we have ut plus a half at squared but from the second equation of linear motion, we found out that s is equal to ut plus a half at squared. So we can substitute for that in our double asterisks, so that now v squared is going to be given by u squared plus 2a. Then the whole of this we replace it with s, so that v squared now is u squared plus 2as. That is our equation number 3, or the third equation of linear motion. Third equation of linear motion. Again, to find that we have actually given the relationship between final velocity, initial velocity, we have acceleration, we have the distance covered, but we have not given the time factor. So in summary, equations of linear motion are as follows. Equation 1, v is equal to u plus at. Equation 2, s is equal to u ut plus a half at squared. And the third equation is what we have had, v squared is u squared plus 2as. Now we look at a few problems related to the equations of linear motion. We look at a few problems related to that. And example number 1. A race car accelerates uniformly from 18.5 meters per second to 46.1 meters per second in 2.47 seconds. determine A is the acceleration and B is the distance covered. The distance covered. Now, a race car accelerates uniformly from 18.5 meters per second to 46.1 in 2.47 seconds. You're supposed to determine the acceleration as well as the distance covered by the car. Now, for our solution, we need to take into account what the question provides for, and u, according to the question, is 18.5 meters per second. V is 46.1 meters per second. Time taken is 2.47 seconds, and acceleration is what we want to get, as well as the distance. Now, we go back to our equations. We go back to the equations. Equation 1, V is u plus at. 2, S is ut plus a half at squared. And 3, V squared is u squared plus 2 as. Now ask yourself, you want to get acceleration. So what do you have and which is the best equation to apply in our case? Now, let us look at equation 1, for example. We have the final velocity. We have the initial velocity. Now, we have time, but we want to get acceleration. If we look at the second one, we have s. And in our case, the question does not give us s. Acceleration also has not been given. The same case applies to equation 3. We don't have a, we don't have s. So for acceleration, the best equation will be v is u plus at. We substitute, and our v is 46.1, which is equal to u, which is 18.5, then plus a, and our t is 2.47 seconds. So we subtract 18.5 both sides, so that 46.1 minus 18.5 is equal to 2.47 a, which is our acceleration, and you find out that 27.6 is equal to 2.47 a. So if we divide both sides by 2.47 and by 2.47, again we get our acceleration as 11.2 meters per second squared. That is part A of the question. Now part B, now we have U as 18.5 meters per second. V is 46.1 meters per second. A is 11.2 meters per second squared, and T is 2.47. Now we want to get S. So we look for the simplest of the three that we can apply to get S. And in our first equation, we said distance factor is not accounted for, so we automatically cannot use that. We go to part 2. Equation number 2 requires us to relate distance to initial speed, time, and acceleration, each one of which we have, and even the third one has initial velocity, final velocity, acceleration, and distance. So we can use either of the two. Now I choose to use equation 3 because to me it's the simplest. V squared is U squared plus 2AS. Then we substitute for each of the factors. 46.1 is equal to 18.5 plus 2 into 11.2, and then S. So these ones are squared. The initial and the final velocity should be squared. Let us square them. 46.1 squared (2125.21) or 42.25 plus 22.4 S. So we subtract to make S the subject of the formula. You take 2125.21, subtract 342.25. We will equate that to 222.4 S. 1782.96 is equal to 22.4 S. We are going to divide by 22.4 both sides, so that our S becomes 79.8. This is distance, therefore meters. Now let us look at yet another example. Example 2. Now, a bike accelerates uniformly from rest to a speed of 7.10 over a distance of 354 meters. We are required to determine the acceleration of the bike. Now, we ask ourselves, what does the question provide? We have the initial speed being 0 meters per second. The final is 7.10 meters per second. The time is not given. The distance is 354 meters. Then acceleration is one we want to get. So we go back to our equations. Equation 1, v is equal to u plus at. Equation 2, s is equal to ut plus a half at squared. And our equation 3, v squared is equal to u squared plus 2as. Now, if we look at the first two, we have the time factor as well as acceleration. And now that we don't have two equations to solve simultaneously, then we cannot work with two unknowns. So that leaves us with equation 3. Therefore, using equation 3, v squared is equal to u squared plus 2as. Let us substitute. V is 7.1 squared is equal to 0 squared plus 2a, then s. Now, 50.41, which is the same as 7.1 squared, will give us 708 a. So we divide both sides to get the value of a. Is going to be 50.41 divided by 708, and we get our a as 0.712. It's acceleration, so meters per second squared. We look at another example. Example 3. A plane has a takeoff speed of 88.3 meters per second and requires a runway of 1365 meters to achieve this speed. It requires that runway to achieve that speed. Determine the acceleration and time taken to achieve the speed. Now, a plane has a takeoff speed of 88.3 meters per second and requires a runway of 1,365 meters to achieve this speed. We're supposed to determine acceleration as well as the time taken. So we start by listing down what we have from the question. And what we have, number one is the initial speed, which is 0 meters per second. The final speed, which is the speed we should achieve just before the plane takes off, should be 88.3 meters per second. Then the distance through which that one should be achieved is 1365 meters. Then we are required to get the acceleration. The acceleration as well as the time. Now, we look at our equations. The three that we have, equation 1 and 2 considers time factor, and time is what we have not been given. Therefore, we settle for equation 3, and using the same, v squared is u squared plus 2as. Now, our v is 88.3. If we square this, should be given by 0 squared plus 2 into our acceleration, which we are looking for. Then the distance is 1365 meters. 1365 meters. Now, 7797 is the square of 88.3 is given by 0 plus 2730 a. Therefore, we divide both sides by 2730 and our a, our acceleration will be 2.86 meters per second. We have the second part. We can use equation 1. You say, but from 1, v is given by u plus at, and we can substitute. Our v is 88.3, is given by u, which is 0, plus a, which we have found to be 2.86, then this one we multiply by t, which we are looking for. Therefore, t will be given by 88.3 divided by 2.86, and this one gives us 30.8. Remember, this is time, so the units are seconds. So we have been able to derive the equations of linear motion, as well as apply them to solve different problems. In our next lesson, we are going to look at free fall and see how those equations will change. Thank you.